So we talked about the packing phase. Now we're going to talk about the finalization phase. So this is when, after the packing, we assign all the final properties. Okay. Um, in addition, we not only specify the final properties like the bonding and its things for everybody, but we also have to tell the system what to do with new contacts that are going to form. Okay. So all of that's going to be handled here. Okay. You may remember yesterday for that cement crown model, we did the same thing in that thing we did yesterday. We added the cement, and then we had 3 classes of contacts. Remember, sand, 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 cement, cement, cement. We had to handle all that. We had to create those guys. We had to give them their properties, and then we had to use the CMAT to specify what the new properties would be if new contacts form, right? Okay. So this is an excerpt from the memo, right? These then are the parallel bonded material parameters. So there's those common parameters, and then there's packing parameters, and then there's also now the actual, basically these are the parallel bond parameters, okay? The parallel bond parameters are going to be broken into the linear group and the parallel bond group. You may remember that the parallel bond has 2 different springs acting in parallel. It has the linear springs for the surface-surface interaction, and it has the parallel bond itself, and they each have different sets of properties. And then B, additional material properties. So new contacts that get formed after this are going to have the linear material. So we're going to do here, okay? Now, one of the parameters that's super important, it turns out, is this thing called installation gap, okay? And so the idea here is that if the installation gap is 0, so here's what the installation gap does. It defines a magic region that's bigger than the ball itself. That's what you're giving, this delta value. And what's going to happen then is it's going to make sure that you have contacts existing between this ball and everybody else that's within this delta distance, okay? So notice if delta is 0, you're only going to have contacts where they're touching. But if delta is non-zero, notice there's an additional 2 contacts here because they weren't touching. Because this then is going to be where you're putting bonds, okay? So the system on the right has a much denser connectivity than the system on the left. We're going to find that this is going to affect it affects the grain connectivity. It's going to affect the modulus and the strength. The bigger the connectivity, the more springs you have. The more springs you have, the higher the modulus. And also, the more things, the stronger it is because there's more bonds in there, okay? This is a parameter, and this is a parameter that I'm providing in this system here, okay? So notice it's not the parallel bond itself doesn't care. It just has parallel bond parameters, but this is sort of a meta level parameter that is incredibly important, that has huge implications for the strengths. Okay. This we're not going to go into in detail. This is telling you in detail what is going to happen depending upon if you have parallel bonded material or contact bonded or flat jointed, okay? This is basically telling you what it's going to do. What's it going to do for these new guys where they're not touching? What's it going to do for the guys that are overlapping? That's what this is all talking about. The basic idea here is that the system is going to set it up so that this bonded configuration has these reference surfaces that are just touching, okay? So if the particles are apart like this and you put a parallel bond in there, what it's going to do is it's going to effectively have cement in between there, okay? What that's going to mean is that there's going to be no effective overlap in the system, which means this initially constructed system is not going to have any forces or moments in it, okay? Remember, when we were doing our earlier work where we just would build a specimen and pack it, we had to pack it. We have compressive forces in there at the contacts. If we go and then just assign properties, that those forces are already there. What we're going to do here is adjust. We're going to adjust the surface locations so that there is no forces. There's no overlap to begin with. So we have a nice clean initial material that doesn't have any locked in forces. Okay. And this is just talking about the parallel bond sort of situation here. Notice in all cases, this is the initial gap, the distance between the surfaces. Here, the distance between surfaces is positive. See those two guys? There's a gap. When it creates the parallel bond, though, it's going to effectively make it look like this, which means that the bond is like perfect and it's sitting there and they're just touching. And it's going to do the same thing. Even if there's overlap, it's going to adjust those local surface orientations such that it's just touching. Okay, that's what we mean. So again, this case, when we're adding bonding material in a gap, it's similar to having the beads being separated at the time we have put in the epoxy. The cement is filling that gap effectively. Okay. The other thing we're going to do at finalization is we're going to do a smoothing operation on the contacts at the interface with the vessel, because they're getting squeezed at some amount, so there's some overlap there. And what we're going to do is we're going to effectively again adjust those reference surfaces so that as far as the contact model is concerned, this is the zero state, and and there's no overlap, so there'll be no forces here as well to begin with. It's as though we carved off these things. As far as the contact model is concerned, that's what it looks like. Okay. So we're going to make two save files. One of them is the final system and the walls are still there. Sometimes then we're also going to do this. For if it's a bonded material, we're going to remove the walls. And now the idea here is this now is a chunk of material that you might do. Like when I did the rock cutting, I built a big giant chunk of material, removed the wall, and then I went and applied the boundary conditions for the cutter and everything. Okay. Here's all this microstructural information, this MP list microstruct props. It's going to talk about all these different things. This is what we went through quickly, the information about here, for example, the bonded materials provide the bond coordination number. That's the number of bonds on average around a particle. Okay. If we use a non-zero installation gap, notice this guy only has 3, this guy has 5. So the bond coordination number goes up. That's telling us something about the microstructure. That's kind of fundamental. So how do we increase the bond coordination number? Well, we can either increase the material pressure or increase the installation gap. For bonded materials, we would increase the installation gap. Okay. And this is what this looks like, right? When you call MP list microstruct props, it goes through the entire system then and computes all these different values, right? So again, number of grains, size distribution is in a plot window, average grain size, stuff like that. That's just for a granular material. For a bonded material, there's more information. So this is a contact bonded material. Yeah. Number of contact bonded bonds, 44, 46. Bond coordination number, 7.5, etc. Okay. Here are these common parameters that are common to all the different materials. So here's where you set the type of material. Contact bonded, parallel bonded, etc. This is the material name it's going to use in the windows. If you don't give one, it uses PFC mat. There's your damping factor. There's your density. stuff like that. Okay. And here's the parameters that are controlling, is it all balls? Is it all clumps? How many size distributions, right? Each one is going to have then, depending on how many size distributions, each one is going to have a diameter range, right? Upper and lower. Diameter is volume fraction. Okay. There's also a parameter in here called the diameter multiplier. And what that's going to do is these other things are defining a size distribution, and this thing will just uniformly multiply all the grains by the same factor. So what this is effectively going to do is shift the size distribution bigger or smaller. Okay, so that way you can give a size distribution and you don't have to change all these upper and lower values. You just give a size distribution. By default, this is 1, but if you make it 0.5, suddenly all the balls become half that size, but they're out of the same size distribution. So we often do this. We build in a system, we can measure its properties, and then we just go and change this one thing. And now that suddenly builds the system. If we make that 1/2, it suddenly builds a system with all the balls half the size. Okay. There's these common parameters. That's where we're setting them. This is the values from that previous table. So this guy has lower diameter, upper diameter, goes from 4 to 6 millimeters. Volume fraction is 1. Number of size distributions 1. So this is a simpler one. Here's density, damping factor, etc. Okay. This is the example of how to, if you have a general size distribution, percent passing from 0 to 100, grain size. This might be a general distribution that you really want to get. And what you do is break it up into bins. Each bin has a volume fraction. So this guy has a volume fraction of 0.1. This guy has a volume fraction of 0.2. And then it goes from here to here. The sizes goes from here to here. That's what this is doing. So this is how you would put in a general size distribution. Okay. We have this ability to generate these microstructural plots that look like this. So for a contact bonded material, so this is that microstructural box. So it's just going to show the balls with centroids in there. For the contact bonded system, it'll draw little lines between them. For the parallel bonded system, it'll draw little cylinders between them. For the flat jointed system, you can look at it like this. Okay. This is the cracking. There's also, from the plot sets, the ability to draw these specialized cracks where the thickness is proportional to the gap. And that's what you're seeing here. Okay, so notice those guys, if there are cracks there, but they're not being currently wedged open very far, but these are. This is the stress strain curve. So this is at the end of the test. You can see what's going on. Same thing happens in 3D. Here's the 3D, actually. Okay. All right. This is another one of these microstructural plot items to draw these cool things. This is the 2D thing. This is the 3D. This is really what the microstructure of the 3D flat jointed thing looks like. That's the mechanics of what it's doing. Okay. One of the things we find when we build these flat jointed materials is, remember when we specify, we have to specify the radius of each one of the flat joint. That's the radius of this thing here. Here we're drawing the radius of each one in its location. And if we set that radius multiplier equal to 1, the radius then will be equal to the radius of the smaller of the two balls. If we set that to 1 for a general packing in 2D or 3D, what we get is we actually get these surfaces of the cement to overlap one another. And that's what it looks like here then. This is, I call this microstructurally invalid, meaning that you couldn't actually construct this system. Because you can't have interfaces of material overlapping each other. It doesn't make any physical sense. Okay. But the model doesn't know about that. It's just going to happily use that and go on with life. This all being said, it still can be a useful model, and we find that using that lambda multiplier of 1 gives us quite reasonable and good results. Okay. Most parallel bonded systems that people have used over all these years for all these different research purposes have always used that radius multiplier of 1. And basically, no one had ever actually drawn plots in this way, so no one ever noticed that these things are overlapping. Okay. So now we have, for the linear material, here's the parameters. There's only 3 things, right? Effective modulus, stiffness ratio, friction coefficient. We use these two to set Kn and Ks, right? That's in material property parameters. Contact bonded material. It has the linear group stuff, which is, again, the same thing for the contact bonds. It has these 3 things. Then it also has these guys. Here's that installation gap that I talked about. And then here is the tensile strength and the shear strength. That's all that it has. And the tensile strength and shear strength are going to satisfy a normal distribution, and you're giving a mean and a standard deviation for these things. Okay, that's what it's expecting here. Tensile strength mean, tensile strength standard deviation. This means there's 2 different fish variable names. That's what the braces mean. Okay. And then again, you have to say what's going to happen for new contacts that form after you built the material. And so here we're always putting in the linear material. And so it has these 3 parameters. Okay. So this defines properly then. So notice there's a lot of stuff here going on, right? There's the common parameters, there's the packing parameters, and there's the specific ones for contact bonds. All of those things are going to potentially affect the material itself. In the world of parallel bonding, here's the linear part. Here's the parallel bond part. Again, there's that installation gap. Here's that radius multiplier. By default, it's 1. For the bonding material itself, we're going to give an effective modulus and a stiffness ratio. So we're giving those both for the surface-surface interaction to set that Kn and Ks, and we're giving those for the parallel bond cement to set this parallel bond cement Kn and Ks. There's this thing called the moment contribution factor. We're not going to worry about that for now. Okay, just use the default. And then there's again, the micro tensile strength distribution, mean and standard deviation, and there's the cohesion distribution, the cohesion and the friction angle at the micro level. Okay. Just a second. I'm just making a note. Parallel bond MCS default equals 0. Okay. And then the linear group. What do you do for the new guys? Okay, so then those are all the properties of parallel bonded material. Similarly, here's flat jointed material properties. One of the additional things for a flat jointed system, and I don't have a picture here, is for every flat joint can have this initial gap that it has. And so we talk about there's 3 types of systems here. And let me actually open up the documentation and show you the picture I want to show you. So I'm going to go to flat jointed material microstructure, page 29. Okay, 29. 29, try again. There we go. It's going to set up 3 different types of flat joint microstructures. You can have some that are bonded, which means the initial flat joint surfaces have no overlap, but they're bonded. Or you can have the initial surfaces have no overlap, but be unbonded. Or you can have some gap between them. And what you're going to do is you're going to specify the volume fraction of each. And it's going to randomly set these things by randomly going through all the contacts, the flat joints in the model. Okay. By default, it just makes everything be bonded like this. So this guy becomes 1. But this is a way of putting an initial set of effectively opened slits and gaps into the system. And these opened ones, you give a normal distribution of gap sizes. Okay. So that's what this is allowing you to do here. That's the bonded fraction. That's the gapped fraction. This is the mean and standard deviation of the gaps. Okay. Then you're controlling the discretization of that flat joint interface. That's what these things are controlling. This is the radius multiplier. Again, it's telling you the radius multiplier. How wide is the radius of those things? Okay. You can either make that be fixed, so the radius multiplier is 1 everywhere, or there's an algorithm in there where you can make it so that it will choose each radius in such a way that it's still microstructurally valid. Okay. Usually you just want to make it be fixed. Here's the effective modulus and stiffness ratio, because we need to get the stiffnesses for that flat joint material. Notice it does not have surface and cement. It's all built into one. There's just one set of stiffnesses, right? Friction coefficient, after it's broken, each element after it breaks has a friction coefficient. And again, tensile strength, cohesion, and friction angle at the micro level for those things. And the tensile and cohesion are coming from a normal distribution. And then again, what do you do after you break? We're going to just put in a linear model. All right. There's a crack monitoring package. What this is going to do, it's going to be tracking every time a bond breaks. It's going to actually take that information and it's going to store it internally as a big giant list. And so it's going to track when a bond breaks, it's going to keep track of who were the 2 guys that were connected that broke, what's the position I was at, all these other things. It's going to be able to use that then to do a visualization of these cracks. Okay. And it's going to keep track. Each crack, it is the type. It's either a contact bonded crack, a parallel bonded crack, and then it's going to have its failure mode, whether it was tensile or shear failure. So there's all these are all global variables then. This is crack information, all of them, all the total number of cracks. This would be crack number PB. So that's a parallel bonded crack, tensile failure or shear failure. So this is the naming convention of these things. Okay. This would be the contact bonded material that we did a direct tension test, and you can see these cracks. It's a separate plot item. It uses something called the discrete fracture network plot item. And this discrete fracture network plot item lets you plot what it calls fractures, which are disks. And so it's using that to throw a bunch of disks at this plot item and allow you to see them. And they're going to be colored based on tensile failure or shear failure. So that same thing, I look at it with the balls on, I turn the balls off. I just keep the grip balls on. There's my cracks throughout 3D space. Okay. This is my 2D model. Same thing. Now my cracks are going to be these lines, right? Contact bond tensile failure. That's what that means. How do we measure stress and strain and porosity? This is the naming convention of the things we're measuring. Okay. We're basically going to compute them with measurement spheres. We're also going to compute them using walls. Okay. And we're getting all these different things: axial stress, radial stress. Okay. And in the manual, it's all described exactly how they're defined and what and how we're getting them. Okay. Stress and strain, we use continuum mechanics convention. Tension is positive, extension is positive. Okay. And so we're basically getting these measurement-based quantities from the measurement circles, or we're getting the wall-based. Notice if we use walls, we can only get the direct stresses, sigma x, sigma y, sigma xy. We can't get shear stresses from walls. But from the measurement sphere, we can get shear stresses. So there are 6 terms of these guys, okay? And the measurement spheres, remember, do not guarantee it's going to be a symmetric tensor. We're going to take the average, and so it will be symmetric, these stresses and strains, okay? So here's a summary of the types of tests that we would do. So here's, and this is just showing it in 2D. Here would be a confined test. This would be the biaxial 2D version of a triaxial test. We have walls all around. For the side walls, we have a servo mechanism that's continuing to maintain a confining pressure, and we move the walls up and down. Notice that we're actually moving both the bottom and the top. We're doing this on purpose because that way we can put a measurement circle in the middle, and the specimen, as we load it, is not going to the middle is not going to move. If we just pushed it from top, the whole entire system starts to move down. Okay, so to keep everything symmetric, we load from top, above, and below. Okay, we remove the sidewalls to do an unconfined compression test. We keep the sidewalls on, but don't allow them to move to do a uniaxial strain test. This is our Brazilian test. We take the specimen and we carve it into this shape by deleting the other particles. We squeeze it. And then for direct tension, we identify particles above and below, and we control their velocities to pull it apart. Okay. So it's the velocity that matters, the velocity of the platens. Instead of specifying velocity, we specify strain rate. Okay. And so the strain rate is related to the velocity with this relationship, where this is the height of the specimen. Okay. So you specify this, it uses this relationship to set the velocity. Okay. As I mentioned, it's really important that velocity, you need to do a test. You need to see your results of stress strain. You need to change the strain rate, make it slower. Keep doing that until you keep getting the same results. Okay, that means you're quasi-static. So here is for the compression test. You can do it in a polyaxial cell, or you can do it in a triaxial cell. And there's 2 phases, just like in a real test. You have to basically apply the initial confining pressure and get everything in equilibrium. That's what I call the seating phase. After that's done, you're going to reset all the strains to 0. And then we're going to do the loading phase. And you're going to basically start to apply axial strain. Okay. And in addition, this loading phase is either going to be a single stage, and what it's going to do is it's going to say it's a UCS test. It's going to just keep on running until the value of the stress, the axial stress, equals some multiple of the value, the maximum value it ever had. So it's going to run the test until it has dropped to say 80% or dropped to say 50%. Okay. So it's going to be able to automatically do that. You're not going to have to sit there and try to guess the number of cycles to be able to get to the peak. Okay. You can also run this so you can just create, you basically tell it stages where you specify the strain. So you can say in stage 1, I want you to apply a negative axial strain of 1% and save the file. Then in stage 2, I want you to apply an additional 2%. And then after stage 3, I want you to open it up a certain amount. And so you can control the platens by specifying increments of strain to be applied again, or you can just run it automatically and have it stop at some point. Okay. During this test, we turn on crack monitoring if it's bonded materials, and then there's all sorts of histories that are being monitored and plotted for different things, right? So there are parameters to control the compression test. right? So here, test type, is it a confined test? Is it an unconfined test? It is a uniaxial strain test, right? Here's the initial confining pressure. Here's that axial strain rate. And I can't stress enough how important it is to make sure that you're getting quasi-static response. I have seen dozens of journal papers where people run these sorts of tests too fast. They get results that they think are quasi-static, and then they make all these conclusions about it, and it doesn't, and it's totally wrong. And so this is really important because everyone always wants to dial up that speed so the test runs. I want it to run in 15 minutes. It's like, well, okay, it's running in 15 minutes, but you're loading it too fast. So this is really important. So what you do is when you're setting up your first system for some kind of material, you do a few runs and play with this to figure out what it needs to be, and then you just leave it at that. Okay. And you would start with the system that we have, the example. And for that particular size specimen, you'd have that. For one thing to be aware of is that because you're specifying this and it's choosing the velocity, as you change the height of, if you make a specimen that's 50 millimeters high and get it all going right for some strain rate, if you suddenly make a specimen that's 1 meter high, you're going to have to actually adjust this thing to get approximately the same velocity, and to be quasi-static. Okay. So be aware of that. What else? All kinds of stuff here, right? What's the, right? Are you going to do a single stage that's automatically going to terminate? If you want to do a single stage that terminates, you have to give it what's the fraction of load at which you terminate, right? Okay. All right. Here's the Brazilian test. It has parameters. What it's going to do is carve out the material into a cylinder. It's going to use these top two walls to squeeze it. Okay. Direct tension test. It's going to identify layers of particles above and below and make them move. So now, come to the examples. So there is this example projects MatGen directory. So there's MatGen P-bond, MatGen C-bond, etc. Okay, those are examples. So what you want to do is start with that. Start with that, run it, look at the behavior, make sure it makes sense, and then use that as your starting point. Okay. And say, okay, I ran this thing and it had a modulus of 10 GPa, but I want a modulus of 2. So then go change the E star to be 2/10 of its previous value and run it again, and you'll be close. And then just keep working from there. Okay. So there's an example in the manual for the linear material, and this talks about how it's being created, what the specimen size, it's being packed at 150 kPa. That's the thing we ran at the very beginning. So it has all these micro properties. So this then is the actual values of all those different micro properties that we're specifying to make this particular instance of a linear material. Remember, common properties, packing, here's packing pressure, right? And then finally, the values of that linear contact model, okay? So that example that we run looks like this. Here's the vessel modulus. Here it tells me, here's what I have in this system. It had 835 grains. It had a porosity of 0.38. This is the average diameter. This is the D50 parameter, average diameter of the grains, the D50 parameter of the grains. All these things come out of that MP list micro struct props. And it's also saying it was constructed at a vessel pressure of 150 kPa, right? This is kind of like the essential features that I've captured in this figure. Here's what we get. We run it, and there's going to be a window, and it's going to give us this deviator stress versus axial strain, negative deviator stress or negative axial strain, right? And so in this particular case, what we did is we maintained a confining pressure of 150 and we applied an axial strain of this much compression, opening, and this much closing. And we monitored the deviator stress and we got this hysteretic behavior. In this particular case, for a granular material, we can take this slope and we call that the resilient modulus. And so notice how you can you make this plot, you put it in PowerPoint, and you can draw these lines really easily. And right off of here, then you can get these numbers for the different plots. And this is just showing, right, the slope of that is the resilient modulus, right? So then again, in the manual, there's the contact bonded material. Here's all the properties that were used for it. Here's what it looks like in 3D. Again, modulus of the vessel. It's a cube, 50 millimeter side length. It was built at an initial pressure of 30 MPa with a 0 installation gap. So this system then, after it got created, has this many grains. This is the contact coordination number, the bonded contact. So every grain on average has 6 contacts. Here's the grain size, the average diameter. Here's that microstructural box. Here's showing the spheres in there. Here's showing the contact bonds as lines, right? Just mentioning again, if you can somehow increase that bond coordination number, you're going to increase the modulus and the strength. And typically what you would do is increase the installation gap and you would get more bonds around each grain. Okay. This is what this looks like. Here's a compression test that was done. When we do the compression test at the beginning, we take these sidewalls and we move them back out of the way so they're not touching. And then we start pushing with the top and bottom. And here we're looking at the wall plot item, we're looking at the ball plot item, and we're looking at that fracture, that DFN plot item. And that's letting us see the cracks. Okay. From that test, we're measuring deviator stress versus axial strain. This is if it's unconfined, this deviator stress is the axial stress. So there's your stress strain curve we measured. We ran this one until it reached 80% of the maximum value. That's when the test stopped. At that point, we made a save file. At that point, that's what this looks like. Okay. Notice also that in these plots I'm making to show, this strain rate is so important that I'm actually putting it there. And it even says that in the title of the window. It says, oh, this is the contact bonded material. It's a compression test. It was run in an unconfined mode. And the strain rate that was applied is this. And this is the end of load stage 1. Right? So from this curve, we get the UCS. We can get the modulus by taking the change in stress over change in strain. Okay. Notice this at the beginning. It's sitting here. It's not sitting at 0 because at the beginning of this test, what do? We pull the sidewalls out and then we have to seat the specimen. We have to apply a little bit of pressure to begin with, and then we start doing our test. So I told it in this case by default to use 0.1 MPa as the initial compression, and then we start the test. So that's why the initial state here is 0.1 MPa, and then it starts going after that. We could have set that smaller to make this closer to 0. Okay. We also plot the radial strain versus axial strain. The slope of that is the Poisson ratio. So notice it's linear. The material is linear pretty much, and then it starts doing cracking. Poisson ratio starts to become meaningless after that happens. So there we go, 0.12 Poisson ratio. Here's the Brazilian test. At the end of the test, it looks like this. This is what we measure, force first displacement. We get the peak force. This is the relationship for converting Brazilian peak force into an effective tensile strength. I'll call that sigma sub B for a Brazilian tensile strength. So we run that through, we get 0.89 MPa. when we did the direct tensile test, we got, where's the direct tensile? I didn't do the direct tensile, sorry. We did that one first, we got 0.89. Then we do the direct tensile test, we're getting 0.6. This is axial stress versus axial strain for the direct tension test, okay? So the Brazilian thing is coming out at 0.89. So the Brazilian measured tensile strength is actually always usually a little bit bigger than the direct tensile strength. And so we're seeing the same thing with our system, okay? The conclusion is that you can build a vast microstructural space here just using this package, which is a very small subset of everything, right? Because it's like, oh, everything has to be parallel bonded. Well, maybe you want some parallel bonds, some not, etc. So this is giving you a way basically to work with PFC to build this particular class of bonded particle systems. Okay, so that's the thing. Here's where I just wanted to point out there is this document in the FISPANC documentation that talks about calibrating flat jointed material. Yeah, there's the beginning of it. Calibrating a flat jointed material. Here's the steps to go through. Okay. Close all tabs. There we go. That's the introduction. That's the overview of the material modeling support package.